Um, my name is Simon Davies. I work as a Windows Azure TSP in the incubation team in Microsoft in the UK. I've been lucky enough to work with some of our early adopters over the last 12 months or so. And what we're going to do for the next 45 minutes is really, I'm going to hand over to those guys to really share their experiences and lessons learned in building their applications. Just before they do that, I'm just going to give you a few thoughts on scalability in the cloud and why it might be somewhat different than scalability perhaps in the data center. And as I say, we'll then pass over to a couple of applications that are somewhat different from each other, two very differing types of apps, very differing workloads, both in terms of scale and in terms of what they're doing. And then if we have time, we'll do some Q&A. I suspect we won't, there's a lot of content, but we can always go out into the corridor afterwards. So, thinking about scalability in the cloud, if we start with a very simple definition of what scalability is, scalability being the amount of work I've got to do divided by the amount of resources that I have, and the idea that by adding more resources, I can do more work. In a traditional data center app, the way you'd think about that is essentially you would understand the scalability potential of a system and understand what its capacity was. Of course, Windows Azure gives us the opportunity to both add and remove resources dynamically. And the remove thing is quite interesting because it sort of changes that whole thought process about scalability. And that, along with the business model, actually, which is the imperative for you to think about giving resources back and using resources efficiently. Some of the things that it changes are the way you think about capacity planning. Capacity planning traditionally is a sort of long-term offline exercise you might do. It's a much more dynamic thing in this sort of environment. Utilization levels are important when you are paying for the resources that you use. If you've invested in your own hardware, then yes, utilization levels are important, but they're not as much of a factor on how much you pay perhaps as they will be in this environment. I think the really important thing is that the definition of scale changes really in terms of the workloads that you have and perhaps the characteristics of the data that you're dealing with. And with that in mind, we're going to have some presentations from two customers who have a web workload that shows off some of the dynamics of having a web application that needs to deal with a varying load, and we're going to show off some details about a background processing application that needs to deal with a huge amount of computation in a defined window. So with that, I'm going to introduce Jim Zimmerman from Thuzy, and he's going to talk about the work that they've been doing with Facebook apps in Windows Azure. Jim.
Thanks, Amy. Hey guys, how you doing? Glad to see you can make it. I saw that line with the laptops, and I think I'll wait a little bit longer. My name is Jim Zimmerman. I'm CTO / lead developer. I write a lot of code for Thuzy.com. And what I'm going to go through for about 15-20 minutes is what we did with our Facebook apps. Does anybody have any apps that are live in Azure right now? Okay, so we have two apps that have actually been live, one since last week and one for a couple weeks now. So I'm going to kind of go through one of the apps right now and kind of go through lessons learned, what we learned throughout the process, and what I can show you guys and what to watch out for when you do go live with your projects. Wait, went the wrong way. So who are we? We develop customized viral marketing solutions utilizing a variety of different technologies, engage users, measure results on, anywhere from app downloads to how many friends you invited to the app, things like that. We also ensure maximum scalability through exploiting the latest virtual computing using the Azure platform and tools. I would not suggest creating Facebook apps without having a cloud backend. The way they viral, you cannot predict how much resources you're going to need day 1 versus day 10. So, that's who we are. So when we were looking at the Facebook app, the few of them, we knew we needed to support thousands of users virtually overnight. We could not predict how many we were going to get hit with initially, but we knew from viral math that it was going to exponentially get higher. So our models predicted the geometric adoption, and that's exactly what did happen. Success of one of our clients could not be the failure of others, so shared hosting was not an option at all. Requirement for distinct computing environments for each SUSE customer, which Azure does very well. Our job is to basically turn social media data into real business information. So we needed to have a robust backend for reporting detailed analytics. With SQL Azure, that's kind of a no-brainer there. Some additional needs we needed. We build cool social media web apps, and we don't know much about running data centers. So we didn't want to have to hire some data center gurus to manage all of our servers. And we didn't want to purchase extra servers just in case, overnight everything goes crazy. We need to add new servers or new virtual machines. We didn't have the infrastructure set up to do that. And consistent user experience was mandatory, meaning every time the page loaded, it needed to be fast, and we needed to make sure that scaled. They don't like to wait, otherwise they'll just drop your app real quick. So we looked at different hosting options. We could have used our own data center. We have 5 servers at our own data center. But what we realized is too expensive and unpredictable growth. It's really hard to plan for. We looked at Google very briefly, but we did look at them, and it just didn't have the familiar programming environment that we were accustomed to. Amazon, we could have used Windows virtual machines and kind of built up our own mini data center there. But it didn't have as many features as we wanted. We'd be kind of back to running our own data center, but virtually in someone else's space. And then, obviously we looked at Azure, and, with all the familiar Microsoft technologies, it's kind of a no-brainer. Especially when we found out that we could go live before PDC. That was kind of the clincher on that, because we kind of have market. It's interesting doing apps for marketing type of apps, because there are real deadlines because of their other marketing commercials, these type of things. So a very different kind of environment. So this is kind of the topology of what our app eventually ended up looking like. You have the Facebook infrastructure that kind of sits in front of all this. And then we have, currently we have 5 web roles that handle all the traffic from the app. And then we have 3 worker roles, one that collects bad emails from an external web service that we find out, which emails bounced, because the Outback app itself sends out coupons by email. So we wanted to know which ones bounced back so that we could send Facebook notifications to that user saying, hey, your email bounced. We tried to deliver your coupon. Could you click here and give us another email address so we can ensure you have have your coupon. That helps. Obviously people posting onto the wall saying, hey, I didn't get my coupon. We were trying to be proactive with customer support there. And then we had notifications worker role that kind of listens on a queue for different Facebook notifications that need to be sent out. And then we have a contact worker role that basically grabs the contacts that are entered off of the queue and go ahead and denormalizes that data and puts it in SQL Azure. That helps for the reporting of things. And it doesn't mess with the live app, because we're storing everything in table storage as the apps run. Okay, so because of the limited amount of time, I'm not going to go through the real demo inside of Facebook. But if you go to facebook.com/outback, you can go through, get your free Bloomin' Onion, and you'll know that that's actually running in Azure. So if you want to pull up your laptops, you can do it now if you want. So anyway, go ahead and check that out. There's another demo I'll tell you about at the end too that you can go check out. So our client is very happy. We've been live for almost 2 weeks, about a week and a half, more like 10 days. And you can see with inside facebook.com, we've successfully got them to the top restaurant and number of fans for the week. Overall, Facebook, I think we're number 8 for the week out of all of Facebook pages. So they're obviously very, very happy about that. I thought this would be interesting to share with you guys too. This is all public information on number of fans and how we grew. We started off with about 27,000 fans on Thursday, November 5th, I think it was. And we've increased to, before the presentation I checked, I think we were at 405,000 fans, which is pretty good. They're obviously very happy. A lot of people are printing in coupons and taking them into the stores and buying more food. So to them, it was a huge success. And they're obviously getting picked up in the press and on different blogs and whatnot. So that helps fuel the growth. But the way the Facebook apps work is, I invite 4 friends, 10 friends to go get a Bloomin' Onion. I post it to my wall, and then my friends see it, and it just kind of virals out from there. So I want to go over some of the lessons I've learned that I think will help when you're creating Azure apps, especially web ones. You want to make sure you trace everything. It's kind of funny because I've been doing web apps in .NET for a long time, and I didn't really grasp the power of using trace listeners in my own web apps. But Azure kind of forced me to do that. So now, next web app I do, whether it's in Azure or not, I'm going to be having tracing everywhere now because this is so useful to play back in time what happened. So, trace your errors, trace information for debugging later to know where you were, what state you were in. If you don't do it, you'll upgrade later as you start to ask questions about how your app is running because you can't really remote desktop into the instances and see what's happening like some of us are used to doing. You can also upgrade it later remotely with the management APIs. I think there was a session on this at 11:30 earlier today about how to do some of this stuff. But now that it's released, you can go to the site and check it out. You also want to track performance counters. The 3 that I would recommend would be CPU usage, requests per second, and memory usage. These are great. So we know if we see one of the nodes go over 80% CPU, or it's hitting 10 requests a second or whatever, we can go ahead and fire up another instance. So it's always nice to see what your roles are doing. And this is very important, obviously, with web roles because you want to make sure that the user's having a good, fast experience. I would also recommend using worker roles to move data from queues to table storage in SQL Azure. This helps with performance also. And it kind of decouples your reporting from your live system also. It also, if you have an exception inserting the data, you can recover from it when you're in a worker role without the user really knowing what's going on. So that's kind of useful too. And obviously SQL is easier to report on, so it's nice from a reporting standpoint. And table storage allows for more scalability also, so you can scale out very easily with table storage. And then deployment, upgrade manually, move into production, use VIP swaps. So I have some other slides. I'm going to kind of get into a little bit more details on each of these points here. Oh, good. Code. So tracing, this is a very basic example. It went into a little bit more detail in that session that was at 11:30, but for the most part, these are just more of my suggestions. When you set your transfer log level filter, set it to error. Don't set it to verbose. Your logs will go crazy, and then you're going to have to change it back to error anyway because you'll have to delete the logs because it's just so much information. And this is if you want to have it automatically scheduled. I actually think you should schedule your errors, instead of manually moving them. And then we just have them transfer every 5 minutes. And that goes with diagnostics and logs. Okay. With performance monitoring, the ones I said before, the CPU usage, the memory available, and the total requests per second. These are the three, I would say, required ones that you would want to do for a web app. Now, if you look up performance counters on your favorite search engine, you will see hundreds of perf counters, and you can put any of them in here. And these are just the ones that I had chose to do. Deployment. My suggestion is upload a new package to staging. The way it works when you deploy to the cloud is you have the staging on the right, production on the left. And what I have found the easiest is you just delete whatever was in staging before, just delete the whole package, and then re-upload a new one. And then that always fires up quicker than an upgrade. But if you do need to do an upgrade, I do suggest manual upgrade so you can watch the process and see if there's any issues as you're upgrading it. This does make it really easy for when you move to production. Now you use the VIP swap to upgrade and deploy it to production. What's really nice about that is for those of you that don't know what VIP swap is, it rewrites the load balancer to swap staging with production. So you bring up, like in our case, all 8 instances in staging, and then as soon as you get all the green lights, you hit swap, the big magic swap button in the middle, and it rewrites the load balancer. So now the load balancer is pointing to all of your staging instances, and then production's now over in staging. Now, hopefully you tested staging before you moved it, but even after that, check production, and if there's any problems, you just hit the swap button and it'll swap it back, right? And what's really nice about this is while you're swapping it, it brings down all those instances in production one at a time while it's bringing up each one in staging. So your users see no downtime at all. And that's probably my favorite thing in Azure is the no downtime for upgrading production. The first time we upgraded, it was very scary because the viral was going like this, but we had to fix a bug, and there was a few graphic changes they wanted to make, and so we swapped it, at midnight. There wasn't a ton of traffic, but there was enough to where it was kind of scary. But the second time we did it at noon when it was going crazy because we were confident that the swap was going to work. So that was pretty cool to do. So now we're not really afraid to upgrade anymore. So anyway, so while you're doing this, there's tools that you're gonna need for managing records and table storage for testing. Like we would have to remove records out of table storage so that we could test the Facebook app and keep using that same user over and over, make sure it worked. So you'd have to remove the record because we only allow one Facebook user per entry type of thing. We also need to be able to download logs from table storage for tracing and perf counters. Again, these tools work great for that. So tools we end up using are Azure Storage Explorer. This is in Codeplex. It's free. You can download that. Allows you to look at all the records, and you can download them to Excel, which is nice. And then there's this Cloud Storage Studio I found last week. And they don't say how much it costs yet, but it's pretty nice because you can do link queries against the table storage to get very specific info when you need it. Because after you have a couple 100,000 records in table storage, you realize you can't query it like SQL. And definitely do not do a count because it will take forever. And so this is why I also suggest moving things to SQL Azure, kind of in the background. So in summary, Azure provides Suzy a competitive advantage. So please don't tell the other social media marketing companies and let us enjoy our 15-minute advantage. So if any of you are interested in trying to win Super Bowl tickets, we just released a Facebook app for Under Armour last Friday. And you can go to facebook.com/Under Armour and go ahead and fill out the entry. And the more friends you invite, the more entries you get. And good luck. Hope you get a chance to go to the Super Bowl. Thanks.
Thanks, Jim. I think that was a great example of a web application that really has an unknown, unpredictable and rapidly growing load. What I want to do now is introduce Rob Fraser from RiskMetrics Group, who's going to be talking about the work that they've been doing with financial risk calculations using Azure. And I think what you'll see here is a completely different type of workload with a completely different view of what scalability means. So, Rob, thanks.
Good afternoon. Good afternoon. Good afternoon. Good afternoon, everybody. That's better. I'm Rob Fraser from RiskMetrics. I'll just be giving you an introduction to what we're doing and why and the problem domain, and then I'll hand over to my colleague, Phil Jacob, who's head of our analytics development, to talk about the actual architectural pattern we built for our particular kind of scalability. I'll start by just outlining who we are briefly. We provide into the financial markets various services. The main one we'll talk about today is risk management. So we do a lot of financial analytics calculations. We also do various kinds of governance and corporate services. What we're doing and why we're here is we're trying to extend our analytics capability out from our on-premise infrastructure out into the cloud. So what are we doing? Right now we're running on about 2,000 instances worker roles on the back end with a plan to go up to about 10,000 instances, 10,000 worker roles sometime in Q1, and then later on through next year, keep that going up maybe towards 25,000, 30,000 worker roles towards the end of next year. The big question we get is why do you need so much computing power? The financial risk analytics market is actually pretty complex. To calculate financial risk, we need to do a couple of quite difficult things. First thing we need to do is do very large-scale simulation of where market factors, market prices will go over time. So that's one level of simulation. Having done that level of simulation, we then need to do further simulations to work out the prices of various complex financial assets. This is notoriously complex and notoriously difficult. You end up doing complex, large-scale Monte Carlo simulations embedded with other Monte Carlo simulations. And the computational demands of this are extremely high, which is why you'll see that financial services firms have typically been always at the forefront of high-performance computing because of this very complex problem space. For us, our particular loading is characterized both by peaks, but also an aggressive increase in the nature and the complexity of what we do. So to give you a bit of an example on the peaks, this is for a month of September. This is broken down by hour, the analytical throughput we had through our existing production infrastructure. And as you'll see, you can probably spot Monday, Tuesday, Wednesday, Thursday, Friday. We have very high peaks. It actually turns out that 50% of the time, our load is less than 18% of our peaks. So we have a very peaky demand infrastructure or demand for our processing infrastructure. More interesting maybe as well is the nature of the growth in complexity. This is this chart goes back to 1994 when we first started, when we were part of JP Morgan. And it's a log scale on the left. This represents approximately the most complex analytical problem we did for our clients. So if we take 1994 as the baseline, this graph shows how the complexity of problems we've addressed for our clients has increased. And to give you an impression of this, Moore's law, so approximately doubling processor capability every 2 years, on this graph has that kind of slope. Our kind of slope is that we've more or less, since we've been founded, doubled the complexity of the problems we've addressed every 6 months. And that's created a very large computational demand, and we've had to build architectures around that. To give you an idea of the kind of architecture we do, diagram here shows the basic structure of what we do, and there's two kinds of simulation regime we have. Down in the middle, in the big sort of purple box, is the data-intensive part. We have large multi-terabyte data stores of market data and market price data. And we have various distributed analytical engines which go and take that market data, do the simulations to generate lots and lots of these market scenarios. We then package those scenarios up together with our financial assets and send those work packets out onto a large grid of pricing engines. Within our own data centers, we have many thousands of CPUs to do that. And all that's done over the Windows HPC server and the SOA broker. Those distributable work packages are quite complex. They contain information on the financial assets and those pricing information for the markets. And to generate the response packet with the results can take anywhere between 150 milliseconds, maybe 30 seconds or more, depending on the complexity of the particular asset. So not only have a large number, many millions of these packets to process, but the actual granularity of processing time varies as well. So we hatched a plot. We thought it would be interesting to see if extending out from the HPC broker, we could add Windows Azure processing resources into this particular grid structure and see if we could scale out this computational part of our processing to the cloud. So we kicked off a project. We hatched a plot in March to do this. We first started talking to Microsoft in July time, joined the TAP program in August. September and October did the main engineering work, and now we're into pre-UAT and UAT testing with production rollout scheduled, large-scale rollout scheduled for Q1 next year. The key part on this has been the last sort of 8 to 10 weeks when we've got into the real architectural pattern. Taking the outline proof of concept we have and really making it an industrializing that architectural pattern. And that's really the interesting thing about taking this computational problem out onto the cloud. So at that point, I'll hand over to Phil, and Phil can talk you through the actual architectural pattern.
So moving into the cloud has given us a chance to rework a lot of old debates once again. Building large-scale computations obviously requires a lot of careful design, and you see the need to avoid recreating the classic von Neumann bottleneck out there in the cloud. As a general sort of observation, the way to try to go about it isn't to come up with a grand plot up front about how you think this thing is going to operate. The way is obviously to reason, come up with a theory, and then have your code well enough instrumented using the techniques that were described earlier and that Jim covered to be able to verify that your theory's right and then advance on to the next bottleneck. Another requirement that we had in moving our application to the cloud was that we were pretty determined that we didn't want to make changes to a very complex piece of analytical code. This code implements a whole bunch of stochastic partial differential equation solvers and econometric models. So we did not want to be cracking open that code, or there's no way we would have achieved it in the in the time frame we did. In actual fact, we probably changed less than 10 lines out of a 50,000 line piece of code to get it up and running within the cloud. The other sort of key feature of what we did was to try and allow something where we could scale each of the components independently. So where we could scale both what was running in our own data center, how we communicate with the cloud, and then the resources in the cloud, all independent of one another. So I've got two sort of slides here now looking at the architecture. The first slide here is sort of our data center side of it and what the pieces are in it. And then we have another one that looks more at what's going on with the communication and in the cloud itself. So as Rob had said, our in-data center architecture uses HPC servers, SOA broker format or framework. And most of the work that has gone in to what we've done in our cloud implementation has been to make the Azure cloud look to our risk analytics engine as much as possible like the SOA broker, and to hide some of the complexity and additional issues that show up from dealing with remote resources. So the piece that we've put the most effort into constructing has been what we call as risk bus server, and this thing is acting as an interface between cloud-based resources and our app. And this is sitting exactly where the HPC SOA broker would sit within our HPC setup. So within the cloud itself, the resources that we're making use of, queues for the communication of work coming in, blob storage to hold a couple of large blocks of data, and we'll talk about that a little bit later. Worker roles for hosting the actual computational engines, and then queues on the way out, and blob storage on the way out for holding additional large data structures. In mapping to the Azure environment, we found that the use of Visual Studio, it gave us a very good handle on being able to construct the application, but it's very difficult to reason about the behavior in the cloud when you're dealing with two processes running locally on your machine compared to trying to get up to 2,000 odd nodes, and later I think we're trying to get to about 10K nodes in the cloud. So it's a functional, you'll see the same functions there, but you can't really scale out from just looking at what's there in Visual Studio. The other key thing I would say is not to be afraid of trying to put legacy applications up in there. Our app is 32-bit .NET, C++, CLI, and it's dependent on a whole bunch of third-party libraries running 32-bit native code. And initially we were a little bit scared that this would cause issues, but was just fine. We had to solve the problem of addressing where we'd initially decided to try and run directly within a worker role, and that wasn't going to work out because of us being 32-bit, but then we switched over to this idea of, well, let's go host this application inside a worker role instead of a web role, and at that point everything dropped into place pretty readily. The only changes we actually had to make to our existing code base were, one, to go and pull a bunch of support files that are truly huge on demand from blob storage, and then putting in a little bit of extra diagnostic information. Other than that, this application required absolutely no changes to its core, and most of the work went into designing that thing that we've called this RISC burst server, and then support code in the worker role around it to feed messages through. So, I mean, what are the issues in getting to the cloud? First of all, dealing with the cloud is different than dealing locally within the data center. One, you've got the bandwidth issue over the internet, and the way we handled that is by making use of the blob resources. One of the sort of key features of what we're up to is we're passing a lot of repeated large data up in order to trigger our calculations. Those repeated large blocks of data, instead of including them directly within the web service call, we've instead switched over to using a call by reference, and then pushed the data blocks up to blob storage. So on the far end within the cloud itself, they're dereferenced by pulling them out of blob storage. And we feel that this is a fairly repeatable pattern for a lot of forms of data. The thing that makes it particularly easy for us is that our calculation involves the cross product of asset securities against scenarios. So every security that we perform the calculation on is going to use the same block of 1,000 or 10,000 scenarios. So this worked out pretty well for us. The other issue that one needs to tackle is communication latency. I mean, as you're firing off WCF messages around the data center, obviously the latency you'll see is probably in the order of about 20 milliseconds. In order to tackle that internet-based latency, we've used queues and package messages together to avoid the per message latency. So we'll talk through that a little bit more in a second. However, there's one thing I should note is that this model in which you have lots of outstanding WCF calls coming in to our risk burst server means that as you increase the number of nodes available, if you package up n workloads for each of the m nodes out there, you're going to end up with n times m outstanding calls at any point in time. So a few graphs of what our utilization looked like. A key observation here is that keeping the CPUs busy required a lot of optimization. The biggest piece of optimization of all focused around accessing the queues and the balance between overworking queues and ensuring that you do have sufficient workload on the nodes to keep them fully utilized. And you can see this pattern there where we haven't quite got that right, and there's a few techniques that I'll talk about in a minute or two, where we've helped to damp down some of that cycling around utilization. So, how to get enough load to keep quite so many nodes busy? This is an insubstantial problem a substantial problem on its own. We spent quite a lot of time on the threading architecture within that cloud-burst server interface piece. As I said, you end up with this cross product of the number of nodes times the batch size as being the number of outstanding calls that are there at any single point in time. One thing that got us a long way towards stabilizing things was the realization that those calls needed to be asynchronous, and that certainly brought us a lot more throughput on the risk burst server piece. The way that that server operates, the incoming calls into the server are batched together, and we create batches of 10 simultaneous workloads. As I said, the thing goes and strips out the large items of data and pushes them separately off to blob storage. Once we've got a full batch, the call that comes in with the 10th request will invoke a call out to push that work packet into an Azure input queue. Inside the risk burst server, we create a map then from the message IDs to wait handlers, so we know where the callback's going to go to. On the completion side, there's a sweeper thread that sort of sits there and gathers up messages that are sitting in the Azure output, our Azure output queue that we've created, and then we use that map to dereference where the wait handlers are to sort of kick off the resume work back in the client end again. And we found that we can scale pretty well to 1,000 or so simultaneous requests on each one of these so-called risk burst servers. Within the cloud, again, thinking about the scaling problems there. You can definitely saturate the queues if you get the ratio of queues to processing nodes wrong. I mean, the queue throughput is amazing, but queues aren't infinite. The capacity of those queues to respond to either put, get, delete requests is not infinite, but it's not a problem because you can scale the number of queues along with the number of nodes appropriately. And this is one of the great things about the Azure solution and why it's so much easier to avoid the bottlenecks than on a single bus kind of architecture. The things that help you as well is in the background, the Fabric controller is able to diagnose when certain queues are very busy, and that the Fabric itself will go and sort out moving your queue off to some independent hardware. One thing that we found that was immensely helpful in avoiding saturating the queues was to put in an exponential backoff algorithm. If your access onto the queues fails and you get an exception there, then use some sort of exponential backoff to avoid saturation there. And as I said, the other thing is putting enough items in every queue, request to avoid doing too many calls into the queues. Another item is amortizing the cost of the I/O required against the CPU time you need for the computation. The obvious thing you need to have in mind, as I keep coming back to, is the implications for what's going to go on all the way back in your own data center, and because you do need to be aware that whilst you're going to increase the efficiency within Azure, you can be creating problems for yourself back on your load generation, and when you're trying to do this mixed model of local as against remote. The final sort of tip that within the cloud that we found very helpful was to carry out any sort of I/O access asynchronously on a different thread than the actual computation. And also to have local per node caches of the information that was being retrieved from blob storage as well, to avoid having to do unnecessary reads from blob storage. Exception management. I mean, when you're building a system quite this complex, I think the governing rule has to be keep it simple. Don't try and over-engineer your exception handling. Our pattern is one in which we just pass all the exceptions straight back cleanly to the ultimate application client and let it figure out what to do about it. The diagnostics that we put something together for the purposes of our initial trial, and we're delighted to hear about all of the features that are going to be coming in this new SDK. That's great, and that a lot of the work that we'd had to hand build around tracking the things that everybody obviously needs to track, like processor load, the amount of times you're going into queues, what's happening with the queues, when we were missing our caches internally, etc., is now all available within standard SDKs. I think Rob. There you go. Right.
Thanks, Phil. I'm obviously not Rob. I did promise those of you who were in the room when we started that we had too much information, so just close your eyes for a minute. One thing I'll say, I was lucky enough to work on that application with risk metrics. I'm not sure we actually said what we achieved there in terms of just thinking about it from a CPU utilization point of view. We had in the region of 85% useful, stress the word useful, CPU utilization across those 2,000 instances. In other words, another way of thinking about that was that we had an effectively linear scalability curve for the work, for the transactions, for the throughput. Now, part of that's because of the nature of the problem being sort of embarrassingly parallel. But nevertheless, I think it's an interesting data point. Anyway, there are a few pointers to sessions here that perhaps would complement some of this material. The top one, I think, is Steve's session, who's in here next. If you want to understand more about some of these issues that have been dealt with in these applications, then I encourage you to go to the Windows Azure Platform Lounge. We don't have time for questions and answers, as I promised, but we'll hang around in the hallway outside after this session. So thanks very much.